am going to explain about single stub tuning. Actually, it is a impedance matching technique. It is a technique to provide impedance matching. Now, what is the single stub tuning? Now, what is a stub? A stub is nothing but a small section of a transmission line. It is actually just a transmission line only. It has got some characteristic impedance, say Z0, and it has got some arbitrary length. This length will decide how the impedance matching is done. So now single stub tuning. So let us first try to, before implementing in Smith chart, first let us try to understand that what do you mean by what is the technique behind this single stub tuning. So let us consider a transmission line. Suppose I am having a transmission line. This transmission line is having some characteristic impedance Z0 and it is terminated by some load ZL. So I am having a load whose load impedance is ZL. Now generally ZL is not equal to Z0 in general. So suppose this is my load plane. So if ZL is not equal to Z0, what happens? There is impedance mismatch, due to which when the signal which is traveling like this, it gets reflected back. So this is impedance matching, in mismatch, impedance mismatch. Now what we do is, we now if we see the impedance along the transmission line, the the input impedance, now input impedance at load end, if now this dot line that you can see, this is the load plane. That means here the load is connected. Now if I see the input impedance at the load end, that means here if I see the input impedance, then this will be equal to ZL. This will be equal to ZL. And if we travel, but if we go away from load and towards the generator, because my generator is here, so I am going away from the load plane. So away from the load plane, I will get some value of input impedance, which will be different. So this input impedance along the length of the transmission line is not constant, it varies, and it varies periodically like this. That means input impedance varies periodically. There is minimum, maximum, minimum, maximum. Like this it varies throughout the length of transmission line. And it has got some minimum impedance and it has got some maximum impedance. That means input impedance. I am talking of input impedance along the length of the transmission line. Now, there is, as we go away from load end, at any one plane, at any one point on the transmission line, I may have an input impedance which is equal to, I may have input impedance which is, I may have one input impedance which is equal to Z0. Input impedance is complex in general, so it is of this form, Z0 plus Jx form. It may be of this form at any point on transmission line. Suppose at this point, at this plane, suppose this plane I am considering. So at this plane, if I see the input impedance, this input impedance is of this form. The real part is Z0, which is the characteristic impedance of the line, and it has got some reactance value. Now this reactance can be positive or negative. If it it is positive, it is inductive. If it is negative, it is capacitive. So X can be positive or negative. Now, if at this point where the input impedance is of this form, the real part is same as the characteristic impedance. Now, here if I connect one small section of a transmission line which is short circuited or open circuited at one end. Suppose here in series, that means here in series I connect one short transmission line. Now this transmission line, once again let me draw. So I can connect a small section of transmission line like this. Here I am connecting a small section. Now this other end, this can be short circuited or it can be open circuited. Means it I can leave it like that also. Like that also I can leave. That means this other end, that means this other end of transmission line is open circuited here. Or it can be short circuited here. I can put a short here. So this short or open circuited transmission line, it will have some length. Suppose the length is Ls. Okay, the length I am denoting by Ls, and the distance from the load end at which we saw that input impedance is Z0 plus JXS. Suppose the distance be D. Okay, I am taking the distance which is D. So you understood at a distance D from load end, the input impedance was Z0 plus Jx form. It was in this form, and so at that point I connected one transmission line in series. This is called series connection. This stub at the end of this here at this plane where input impedance was this, I connected one stub in series. This stub is short circuited, it can be open circuited also, and its length is Ls. Now we know that if I see the input impedance of the stub, you see this arrow here, this input impedance if of the short circuited and open circuited line will only have the imaginary part. We have seen the derivation. So suppose the input impedance is ZS. ZS is the input impedance of this stub. So the input impedance of this stub ZS will be of the form J, only J term will be there, isn't it? We know what, for a short circuited line, what is the input impedance of a short circuited line? That is, here only I am showing input impedance of short circuited line is JZ0 tan beta L. It is JZ0 tan beta L. L is the length of the stub, so Ls, here length is Ls, and Z0 is the characteristic impedance of the stub. So stub impedance, characteristic impedance also I am taking as Z0 only. Now this is actually J, I can write it is J of XS, suppose J of XS. So this is the input impedance of the stub. Now, so this XS depends on the length of the stub Ls. So I can always adjust this length of the stub. This length of the stub I can always adjust so that XS is negative of X. That is, this input impedance, it was Z0 plus JX. This, so this XS, if it is negative of X, then what is the total input impedance? See, here my input impedance is Zin, and I am connecting one stub in series. That means the total input impedance will be added. That means whatever input impedance I am getting for this will be added with the input impedance of the stub. Suppose this input impedance I am calling it as dash, ZIN dash. So ZIN dash plus ZS, that will give us the total input impedance at this plane. Okay, so at this plane, say at this plane, I can consider